Okay. Is my video screen working? I don't see my.
Yes,
okay,
yes.
Okay, I see. Okay, thank you.
It's working.
Yeah. Okay, I think I can start, I guess. Hi, everyone. My name is Shivaraj Kandhaswamy. I am from IUCAA, Pune. Before coming to IUCAA, I spent a lot of time at the LIGO Livingston site in US. So here, today I'm going to talk about two aspects of advanced LIGO. One is detector characterization and the other is calibration. Under detector characterization, I'm basically going to focus on the data quality of the data that comes out of the advanced LIGO detectors, but I'm not going to focus too much on the instrumentation aspect, but I might have a couple of slides on that. Okay, so we can start with this slide where we talk about how we find the gravitational wave signals in LIGO data. If we know the signal model very well, then the theories there is a theory that says that we can use matched filtering to find these signals, and that is an optimal way of doing it. So in here, what I mean by matched filtering is that the inner product of the waveform that we are looking for with the data. So whenever there is a similar signature in the data, then you get higher values for this inner product. Then that is indicative of that kind of signal present in the data. The merger signals from compact object falls in this category because we are able to model these CBC signals very well, either using numerical relativity or post-Newtonian approximations, which are part of the general relativity theory. So in all the signals that LIGO has detected so far falls in this category of CBC, so that they are merger signals of either binary black holes or binary neutron star or neutron star black holes. So here, so far we have detected around like 50 of them. Generally, these signals last like a few seconds in the detection band of LIGO, that is from 20 hertz to a few kilohertz. So if I take this, so this is for the 3 observing runs. If I convert these 3 observing runs to some kind of like time estimate, then it comes around like a year and a half of coincidence between at least 2 detectors, Hanford, Livingston, or the Virgo detectors. This corresponds to almost like a 50 million seconds of data. As I said, we have detected so far 50 binary signals. Each binary signal for in a like almost like a 50 million seconds of data. So it's almost like a needle in a haystack. So so this is very difficult task, and also the task becomes much harder if we actually don't know the model parameters of the CBC signal. That means we have to construct many different waveforms so that we will at least find a match for one of them. So in our case, we basically look for waveforms of the order of like 100,000 or more. So that means we have to look through this 50 milliseconds of data that many times. Also, the data that we get from the detectors are not quite Gaussian. As I said in the first slide, if the data is Gaussian, then you can use to match filtering is the optimal way to look for signals. But our data is not quite Gaussian and also non-stationary. So here is a time series from a short time series from the Hanford detector of 20 seconds duration. On the right side is the distribution of that signal. And you can clearly see that it is not quite Gaussian. This is a Gaussian fit I have. And you can see there are excess on both sides. So the data is not quite Gaussian. So because of these issues, what happens is that when I try to match the data with a particular waveform, I always get some kind of SNR. I don't get 0 when there is no signal. I get some values for the inner product. And if I set a threshold for like if the inner product value has to be above this value to be considered as a signal, sometimes even like random noise in the data can produce that trigger. So we call that false significant event in our data. So they are not actually gravitational signal, just that by random chance we get an excess in the inner product. So how do we differentiate those signals or those events with actually true gravitational signals? There are many ways to go about it. So in this slide, I talk about something that we use based on the signal model. So if we know the signal information about the signal, then we can use that to differentiate between the actual signal and what we get from random fluctuations. For example, for the CBC signals, we know that the frequency and the amplitude of the signal should increase as the time evolves. So that we can use that property to differentiate between CBC signal and the random fluctuations. So here on the bottom, there are two plots. One on the left is the binary black hole signals in the frequency time spectrogram. On the right is binary neutron star signal in the frequency time spectrogram. You can clearly see that as the time frequencies in the y-axis and it increases, and also see that the signal becomes stronger. So the more yellow means the signal is stronger. As you can see, it gets more yellowish as we move towards right hand side in the time. So these two properties that we can use to strengthen our identification of CBC signals in our data. And also we can require additional consistency to say that what we see in one detector has to be consistent with the other detector. So this also we employ. So all these things are based on like signals. So how the signal should look like in one detector and how the signal should look like between multiple detectors. So these are signal-based information that we can use to discriminate between false and true events. But there are also other options like using additional witness channels to differentiate between the false and true events. In addition to the gravitational wave strain channel, each observatories record many different informations that's happening around the site. For example, in the plot here in this slide, at the top is the gravitational wave strain data that is sensitive to gravitational signal as well as other environmental effects that's happening at the site. At the bottom, there are two data from two sensors, the wind sensor and the microphone that looks for like sound signals. And these are not sensitive to gravitational signals, but they are sensitive to the environmental signals. And if you find something in the strain channel, and if there is a coincident signal in any one of the other witness channels, then we could be very confident that that was not a gravitational signal, but that was produced by the environment around the site. And that's why we also see a similar signal in the corresponding environmental channel. So in this plot, we see excess in the HFT channel. At the same time, we also see something in the microphone. So then this basically suggests that this is probably not a gravitational signal, because we also see something in the microphone which is not sensitive to gravitational signal. And you see something else here, and you don't see anything in the corresponding these two channels, then this gives us confidence that this is probably not due to environment, at least not due to wind or sound. So then if we basically eliminate the possibilities, then we can say that it might be due to gravitational signal. And the next one is there is a coincidence between microphone, so we disregard it. And the last one, there is a coincidence between the wind sensor, so we also disregard this particular event. So there's only one that we say could have been a gravitational wave signal. Then we also do other consistency check, like for example, whether we see the same signal in the other detector, and also whether it is consistent with the signal that we expect. So we do further checks, but this is the basic checks that we do at the beginning. And this method is suitable for all signal. You don't have to know the exact signal model. So here I don't have to know exactly what signal model, but if I see the coincidence, then most probably I will disregard this in our strain channel data. So the detector at each site records almost 200,000 channels in addition to the strain channel that is sensitive to the gravitational wave signal. And these 200,000 channels also comes from many different things. Either it could be environmental signals, or it could be various subsystems that make up the interferometer. So here is a layout of the LIGO interferometers. And you also see pictures of various subsystems that make up this interferometer. You start with at the far left, you start with the laser, and that laser is conditioned using the what we call the mode cavity. So basically conditioned, and that is fed into the interferometer. So there are also various cavities that enhance the signal. So here we have what we have is the power recycling cavity that basically increases the power that coming into the interferometer by a factor of 40 for the current interferometers. And this signal is also further enhanced in these Fabry-Pérot cavities, which is sensitive to the gravitational wave signal. Then the signal comes out through the signal recycling cavity, then goes through the output mode cleaner, which also cleans the light that comes out of the interferometer. So there are a lot of cavities that's involved. We do record the signal from all these different cavities. Here I want to note that these cavities are not sensitive to gravitational wave signals as like this Fabry. So if we in one of these cavities at the output, then we could say that maybe something happened in this cavity that changed the output light at the interferometer. So we don't believe what we see in the interferometer at the output as a gravitational wave signal. So this could be one of those channels as a witness channel to say whether we see gravitational signal or not. So here is another layout of this the same interferometer. So there are like 5 main degrees of freedom in the interferometer that that affects the operation of the interferometer. The first one is we start with this Perkel, which is the power recycling cavity. This is the power recycling mirror, and these 2 mirrors. These 3 mirrors form the cavity. That's the power recycling cavity. The main purpose of this cavity is to enhance the power that's going into the interferometer. And there is the other one, Michelson, simple Michelson. This is basically formed by the beam splitter and these 2 mirrors. This is the Michelson, and the next one is the signal recycling, formed by the signal recycling mirror and the 2 input mirrors. And there are two cavities, differential arm and common arm, that's formed by the 2 arms in the interferometer. So there are 5 main degrees of freedom that that we need to control in our interferometer. But only this differential arm degrees of freedom is sensitive to gravitational wave signal, but not the other degrees of freedom. So in principle, these other degrees of freedom as witness to say if there is anything happened in the interferometer that affected the output signal at the output port, and that could have caused a gravitational wave-like signature at the output port. So apart from these subsystem signals, as I mentioned earlier, we also record a lot of information about the environment. We have seismometers, accelerometers, microphone, magnetometers, wind sensors, and even temperature sensors. So we have many sensors, different aspects of the detector. So here is a pictorial representation of and also various sensors that are placed in different parts of the detector. Here is a list of the sensors. As I said, you have accelerometer, microphone, temperature sensors, magnetometer, seismometer, and also like a voltage monitors, whether there is power fluctuation in the power that's coming to the side. Also infrared low frequency microphone. So there are many different sensors that we have placed, so we basically continuously record the data from these sensors along with the data from the output of the interferometer, which is sensitive to gravitational wave signal. So in principle, what we can use all these channels as a witness channels to eliminate any spurious gravitational wave-like signal in our data. Before we do that, it is also important that we understand the relation between the witness channel and the strain channel, because maybe there is a just because of just coincidence, something happened in the witness channel and gravitational signal happened in the HFT channel. So by coincidence, that can also happen. So in that case, we don't want to eliminate the observed gravitational signal in our data. So here is an example of that situation. So here is an HFT. This is a strain channel, spectrogram of the strain channel. On the right side, this is the spectrogram of the microphone in the laser room. And you can see the structure that we see in the microphone is the same as the structure we see in the strain channel. So we can say that they are related because we see similar structure in both of them. And this happened during the first observing run. I will play the sound of this signal. Most of you probably will identify it. So that's basically, there was a phone that was kept in the PSL, the laser room, and they forgot to disconnect it. So someone probably got a random call on that phone, and it rang, and it produces and that also affected the strain channel in our detector. Now we want to know how it affected, why a sound signal affect our strain channel. So there are a lot of mirrors that we have kept on the laser room that basically takes the input laser and points into the interferometer, basically into the cavities. And in terms of that, the table is at a different level than the mirrors. So we basically use this projector to take the beam that is on the table into project into the interferometer. And there are mirrors at the bottom of the top and bottom of this periscope. This is to basically point the laser into the interferometer so that we can align it better. But these mirrors can also be affected by the sound waves in the room whenever there is a significant sound, and they will make mirrors oscillate. And in that way, they will also make the alignment drift, and that will cause the light fluctuation, which would then it would look like a light fluctuation at the output port, and that's what we are seeing here. So that's how a coupling of the acoustic signal to the laser light transform into a fluctuation that we see at the output port. So this is so this coincidence between this microphone and the HFT channel suggests that whatever we were seeing is just coming from the environment. So we basically neglect it for analysis. Where we are looking at an accelerometer in the different parts of the interferometer. So corner station is where the beam splitter lasers are there, and EX, EY are the end station where the two end mirrors are there. So we are looking at the accelerometers in these three locations, and at the same time we look at the HFT, the strain channel, and we see some excess in the strain channel at the same time where we see an excess in the accelerometer. So in these cases, then we identify that so these excess in the strain channel basically happened due to some environmental effect that affected both the accelerometer and the strain channel. So this was happened during one of the rainy days. So there were thunderstorm that produces this excess noise in the accelerometer as well as cause the fluctuation in the output of the interferometer. There are also strange, interesting glitches, things that can affect the interferometer. For example, at both like LIGO observatory site, Hanford and Livingston, we use liquid nitrogen to cryotrap any molecules or gas molecules that try to enter the vacuum chambers, because at the joints of two vacuum chambers, there is possibility that external gas molecules will try to enter. So we produce what we call cryotrap, so that we apply very low temperature system for like liquid nitrogen to arrest any movement of the molecules. So here the liquid nitrogen tank is outside, and we send the liquid nitrogen through pipes, and on those pipes, because of the cold nature of the liquid nitrogen, the moisture forms around the tubes, and sometimes it becomes ice. In summer days, at least in Hanford site, it becomes very hot. So nearby birds, they come and sit and try to eat this ice. So here is a pecking up by the crow there, trying to eat some of this ice, and these vibrations travel through this pipe and affect the suspended optic and produces excess noise in the output of the interferometer, producing like glitches like in the output of the interferometer that might look like some kind of a gravitational signal. So people, it took some time to like identify this cause. Then finally people realized that the relation between what's happening here and what we were seeing at the output of the interferometer, then they went and tried to fix this issue. So there are some strange incident happens like this, that initially we are not able to identify why we are seeing this excess signal in the interferometer. Then it takes a lot of effort to identify the cause. And also we do a lot of hardware injection. Basically, we simulate gravitational wave signal data in the interferometer and see if the witness channel that we are using is also sensitive to weather gravitational signal, because the premise of all these things is that the witness channel is not sensitive to gravitational signal. Only the interferometer, the strain channel is sensitive to interferometer, the gravitational wave signal. So we are basically verify that by doing hardware injection in the instrument, which is basically injecting gravitational like signal in the interferometer. So what does these data quality studies help? How do they help? So here is an example. So the red curve is the triggers. Basically, when I apply a match filtering, I get some values for the inner product, and if I put a threshold on that inner product, if it crosses some value, I say it is considered as a trigger. So this is the trigger I get from my match filtering process. And here is the blue line is the potential gravitational signal dubbed as this number. It happened during the first observation, gravity. That signal, the inner product values of that signal was around this value, and we got inner product for very. This is the distribution of the all other inner product value that we got. And you can see this event is within the values of the inner product that we get from other things. So it could be, we can say that it could be some random fluctuation because it is within this distribution. But if we apply these vetos, like if you look at the witness channel and make sure that there was nothing happening during that witness channel time, and if you remove the times if there was something happened in the other witness channel, then this red curve becomes this blue curve. But this event stays there itself because it's a gravitational signal. It is not affected by the vetoes. So the values of the gravitational signal SNR stays there, but the SNR of the all other signals comes down. At least we remove the SNR of signals with SNR larger than this, because there was some witness channel that was suggesting that it was local, like happened due to something in the surroundings. So we basically go from red to the this brown distribution of the triggers. So this is just from the random, and you can see this what we see with the event. It has SNR that is much further than the distribution. Then we can confidently say that this is a gravitational signal because it is not falling within the expected distribution of random fluctuations. So that's how we assign significance to this signal. So from going from the here to here, the significance of that signal went from 1 in 320 years to 1 in 83,000 years. So the significance of these events significantly increased after applying these vetoes. And here in the other case, where initially we said, oh, there might be a gravitational signal. This is the strain data on the left. Then we sent out the alert, and after some time, when looking through all other channels, we found a channel that had similar signatures, and we expect that this channel is not sensitive to gravitational signal. Then people realized that maybe what we saw in the gravitational channel could be caused by the same thing that caused the change in this auxiliary channel. So we say that what we initially identify as a gravitational signal is not actually a gravitational signal. It is something that happened locally at the interferometer sites. So basically, then you say that that alert is not correct. So in one case, we basically say increase the significance of the true gravitational signal. In the other case, we identify a false event. Then we retract that event based on the other further studies. So it helps both ways. So there are many different glitches that we have identified during the past few observing runs, and these are the some type of glitches that commonly seen in the last two observing runs, O2 and O3, and they affect how we can detect the gravitational signal. Also, the parameter that is estimate about the detected gravitational signal. So both of those things are affected by these glitches. So there is a large effort that goes in like identifying these glitches and removing them from the data. So as I mentioned, a lot of effort has to go into identifying these different glitches and also identifying the channels that can be used as a good witness channels. And so this information is also provided to the outside community through the Gravitational Wave Open Science Center, which provides the data collected by the LIGO. It also provides these data quality cuts so that people can apply these cuts before they look for the signals in the data. And also there are a lot of work effort is spent on identifying these different type of glitches, because the first step in doing removing these glitches is to identify them and see if we can identify a source of this signal. If you find a signal of similar some categories of that happens many times, for example, if the signal only happens in the daytime, then we can say that okay, maybe something that happens in the daytime affects produces these signals, and then we can go and look for sources of that kind. So the first step in removing these glitches is to identify these glitches in the data and classify them in some common categories. So that is what happening now at in the collaboration. So we are not just like using the codes, we are also now using new machine learning codes and also getting help from the people. This is very important if you want to detect unmodeled gravitational signals. For CBC signals, we know that the signal has some certain, and here you can see these glitches don't have that shape. So we would be confident that if we see a CBC signal and if we see something here, we can differentiate between them. But if you are looking for some unmodeled gravitational signal, we are not sure whether this is a gravitational signal or this is something happening in the instrument. So to detecting this unmodeled burst gravitational signal, it is important that we remove all the glitches in the data. So as I mentioned, the classifying glitches is the first step in removing the glitches. So there are many different ways we are trying to achieve this. We are using machine learning tools also to do this, but also getting help from the citizens. So there is a citizen science project called Gravity Spy, where we have put whatever the glitches that we have identified in the bank, and people can go and look at these different kind of glitches and classify them in some common category, so that we can identify how often these glitches happens. Is there a temporal is there a time dependence is there, or is there temperature dependence? Is there any particular dependence, so that we can further go and investigate that particular source for the particular type of glitches. Okay, so I have got a question. I just go through the couple of slides, then I'll take questions. So apart from like identifying glitches, we can also subtract the glitches or even persistent signals persistent noise in the data. So this is done through the what we call linear filtering, or even we do nonlinear subtraction. So the figure on the right shows during the observing run 1 at the Hanford detector. There was excess noise. Here on the left side, you can see this picture. The blue curve is the excess noise that was happening due to some pointing issue of the laser at the input port. And there was a witness channel that was monitoring why this pointing issue was there. And using that witness channel, we are able to subtract out this noise in the data, and we get this blue curve. So as you can see, lower the curve here, better the chance of detecting signals. So we are basically improving the sensitivity of the detector by doing this subtraction. And apart from these glitches, there are also a lot of lines that happens in the detector. So the blue curve is during the red is during the OAT1. As you can see, there are a lot of large lines that large SNR lines that you see. This means that if you are looking for a gravitational signal that is like a narrow line gravitational signal, for example, from pulsars, then because of these different strong lines, we won't be able to identify gravitational signals at these frequencies. We can only see gravitational signals at the different frequencies, the narrowband signals. But there are a lot of improvement that has been done from one observing run to next observing run. For example, the blue curve is for the next observing run, the O2, and you can see that after a lot of effort, we are able to remove a lot of these large lines that we saw in O1. So there are a lot of instrumental work also that goes on to identify these noises. Either they could be glitches that happen short duration, or they could be lines that persistent for a long time. So we basically do many of these identification efforts to remove both glitches and the lines in our data. So this is basically the end of the detector characterization part. I can take any questions at this point on this topic. Okay, I have a few questions. One from Arpita on what other glitches. So I have mentioned a few glitches that we have seen. So if you go to this Gravity Spice web page, you will see the list of all other glitches that we have seen so far. So the question is, if the instrument malfunctions due to some reason, that can create glitches also. So yes, so instrumental malfunction also can create glitches. But we also want the instrument to keep operating. Sometimes if it malfunctions, it doesn't operate anymore, then we don't have to worry. But the only time that we have to worry is that if the instrument malfunctions, but the instrument is still operating okay, at least in some range. So that's where we have to worry about these glitches. So that time we basically look at these other witness channels to make sure that they don't detect anything at the time. And for example, these different cavities that we have in an instrument, if there is a malfunction, generally they will have some signature of those malfunction in them. So basically looking at the signal of those cavities, then we would say the instrument was not working as we expected. So we don't trust the data at that time. So that's the main way that we identify the problems. The next question is Shamik Datta. On how does the weight of the test mass mirrors affect the detection of gravitational waves? So there are lot of, I don't know, but you might have heard in the previous lectures, the noise sources that decides how we get the this shape of the curve. So at the low frequencies, at least currently we are dominated by the technical noise sources. But in the future generation detectors, the low frequency curve will be determined by the what we call the radiation pressure noise, and the radiation pressure noise is inversely proportional to the mass of the mass of the mirror. So the higher the mass, the lower the radiation pressure noise. That means the lower the curve. So that means we would be able to see signals better. So in that way, the test mass mirrors affect the detection of gravitational waves. Basically, they are responsible for one of the noise sources in this curve. The next question also from Arpita: what is the citizen science project which you showed regarding identifying the glitches? Is it available for public to take part in? Would love to join. Yes, so this is citizen science project. I think not only in gravitational waves, it also exists in other parts of other categories of sciences. So here, at least in LIGO, in the Gravity Spy, you can go gravityspy.org. Is the this is the web page link. If you go there, and basically it will give you a list of these glitches, and you have to classify them. So one of the issue is that, as I mentioned, the first step in identifying the sources of glitches is to classify them and see if there is a particular category that happens often, so that we can first go and fix that particular class of glitches. So this classification is the first part, and here in this web page, you'll find all the different kind of glitches that we are seeing. So there is a code that automatically outputs this image, and some user has to go in and he has to classify. Yes, it is like the Zoo Universe project of NASA. Here in this case, we are basically classifying the different kind of glitches that we see in the instrument, so that we will get some information about, is there a particular category that dominates this list, and if there is any particular distribution, temporal distribution, some dependence that's there for this particular glitch, so that we can go and fix this. Because most of the time it's very difficult to identify just looking at the glitch why it happened. So we need more information, and this is a way to generate that different information. Okay, there were some hand ups. Not sure. Sachin, can go ahead. Sachin Dubey, you want to ask your question? Please go ahead.
Okay, thank you. So my question is from that slide, the advanced LIGO length control. On the output mode channel, we have like so many reflectors instead of the other 3 channels. Like you can see, we are used like 3 or 4 channels. What is the purpose of those reflector?
These ones here.
Yeah, output mode channels.
So this is, so one is that you need to form a cavity. The cavities are basically kind of filters. So as I said, this is an output mode cleaner. It cleans the lights that comes out of the interferometer, so that we are only looking at the light that is affected by the gravitational signal. So you need to form a cavity. So cavity, generally you need at least 2 mirrors, but here we have 4 mirrors, so that the light that comes, if I have just a 2 mirror, what happens is that light that comes inside can also reflect it back and go in. So here we have these 4 mirror cavities, such that it is easier, the light comes in and it will gets out from this direction, so that the effect of the light that's going back can be easily reduced. So this is basically different configuration of cavities that one can build depending on the requirement. Here in our requirement, the reflected light should be reduced, and that's why we use this kind of cavity. You can have 2 mirror cavity, 3 mirror cavity. So here you can see 3 mirror cavity at the input port. So we use 3 mirror cavity to clean the light. So here we use the 4 mirror cavities, and the fabric probe is actually a 2 mirror cavity. So the different type of cavities one can form depending on the situation.
Okay, so why don't we use like spherical cavities or something, like spherical reflectors, instead of that direct like flat one? Why don't we use a spherical one?
These mirrors are mostly flat, curved only. In the picture, it looks like a flat, but they are not flat.
Okay, and I'm talking about like suppose there is only one small opening into that a spherical one, and it comes out of the another. So just it goes with the multiple reflection, like how we see in total internal reflection there.
But so here we form the cavities so that the size of the mirror can be small. But if you want to form a cavity with multiple reflection, and if it is just like a delay path interferometers, then the size of the mirror has to be large. But many of the time we can't afford it. So that's why we form cavities of this kind, where there is no opening there. The light comes in because of the properties of the mirror.
Okay, thank you.
Okay, if there are no other questions, we can move on. Not much time. Okay. And now the next part of the talk about the calibration. So here is a picture that you might have seen in other papers of gravitational detectors, where you see a spectrum of the output of the interferometer. Here is it is the amplitude spectral density as a function of frequency. So as you can see, there is a number associated with this amplitude spectral density. There is a number 10 to the power 23, 22, and on the bottom you have frequency. But what we actually see in the interferometer at the output is just a light fluctuation. The light comes out of the interferometer, it falls on the photodetector, it produces some voltages. Then how do I go from this voltage to these numbers here on the screen, which says that this much strain? So this process of going from that voltages to this strain values is called what we call calibration. And in LIGO, this happens. So we have set up the pipeline so that it happens very fast. So at the level of like 5 seconds to 10 few seconds, it happens, so that we can use this data for like analyzing data in real time and sending alert to telescope, optical telescope, so that they can do follow-up. And so this data is also received by the, as I said, for the follow-up, received by the rapid analysis pipeline that look for these signals in the online, so that follow-up can be done easily. So as I said, generally 5 seconds, but we also do calibrations, offline calibrations that takes a little bit more time, but it is a little bit more, have more precision than what we do with this in online calibration. But in general, the calibration is that is basically taking the light at the output port that we record in voltages to converting that into strain. So here, so there are two quantities that we generally use when we talk about the interferometers: the length fluctuation and the strain. They are related by just a simple expression. The length fluctuation divided by the length of the arm is the strain, and this length of the arm is constant. In for LIGO interferometer, it is 4 kilometers. So the length fluctuation and the strain can be interchangeably used. So when I say length fluctuation or strain, they mean same thing because they are connected by a constant factor. So for example, when a gravitational wave goes through, what happens is that it changes the length difference between the two arms, and because of the length difference, you see some light fluctuation at the output port, and it produces some voltage fluctuations. So in let's see. Okay, so here, let's say if you didn't have any controls, you might have heard from the previous lectures that we need to keep the length of these arms at some constant value so that the light can resonate between these in these two mirrors. Between these two mirrors, only by doing that we can increase the total power in the arm. So the sensitivity of the gravitational wave interferometer is proportional to the total power in the arm. So if we can keep these mirrors at integer multiples of wavelength of the light used, then the light will build up in the arms, and we will get large power in the arm. That means the sensitivity of the instrument will be large for gravitational signal. But the moment, if anything, that moves the mirror away from that resonant condition, the light will decrease, and the sensitivity of the instrument will also decrease to gravitational signal. So we basically, that means we are constantly keeping the difference between the mirrors to a very good fraction of the wavelength of the light that used. So that happens constantly. So if, let's say we are not doing that. If we are not doing that, then what happens is that we can use an external signal. Let's say here photon calibrator, which I will talk about later. So I take a photon calibrator, which is basically an auxiliary laser that I shoot at one of the mirror. Let's say this mirror, I shoot an external laser. I know the laser power. Then I know how much the mirror will move. And by that, I know how much the differential arm length between these two arms change. And that will produce some output light at the output light fluctuation at the output port. That is called the Darm error. So I am applying some light, and I know how much that light should change the length of this arm, and I see some fluctuation at the output port. Then basically, then I calibrate this output port fluctuation to the light to the length fluctuation that's supposed to this light produce, this external light produce. And so let's say I'm injecting something here, I'm recording something here, I'm taking the ratio of these two, Darm error by this delta L reference, what I am producing, that gives the response of the interferometer, which we call here sensing function. Then by using some measurements, I can calculate what is the sensing function of the interferometer. Then I model that. So I call this sensing function model, C model. So once I have modeled this, then I remove this precol laser and I let the instrument run, and a gravitational signal comes in and it produces some fluctuation at the output port. Since I have already calibrated this output port using a known length fluctuation, by using this model, then I can get back what was the length fluctuation produced by the gravitational wave signal, which in turn will tell us what is the strength of the gravitational wave signal and also the source properties of the gravitational wave signal. So this is a calibration that we generally do for many systems, where we input something known and record the output and basically calibrate the output using the known input and use that calibration to look for signals from other sources. So this is simple if there is no control happens in the interferometer. But as I said, we do control because we want to keep the light resonant in the interferometer. So because of that, there is other parts that comes in. So we take the signal at the output port and we apply some correction to that field signal, and we use an actuator. Basically, there are controllers in the suspension that move the suspension such that the arm length of the cavity remains fixed. So this basically has a closed loop. So this is a closed loop operation that keeps the length of the arm fixed. Because of this closed loop operation, I cannot just use the sensing function alone to predict what was the gravitational wave signal that impinged on the instrument. I also need to know what is the correction that I'm applying to the arm. So if I do a loop calculation, for example, this is point delta L residual here is basically sum of delta L free is basically gravitational wave signal falling on the instrument, and delta L control is the control signal that I'm applying. So this signal is the sum of these two. Then if I want to know what is the delta L free, what is the effect just due to the gravitational signal, then I can rearrange this and I will get this equation. Delta L free is what I measure, delta L residual, and what I apply, delta L control. Delta L residual is related to Darm error by just this sensing function, which I have already modeled. So I can get this delta L residual, and I need to know delta L control. So I need to model this actuation function of the instrument. So if I know what is the sensing function model, and if I know what is the actuation function model, then using this Darm error and this Darm control, these two signals, I would be able to reconstruct the gravitational wave strain. So initially we already said how do we see this sensing function. Now we look at the actuation part. Actuation part, as I said, we control the mirrors. We control the mirrors not just like only one point. We control the mirror at many different positions. The mirror is like a 4-stage suspension. So we can move the mirror at 4 stages. All of them will move the bottom mirror where the light is reflected and forms the cavity. So there are like 3 stages. Here we have used only 3 stages. But in practice, there is also other stages, but they don't affect this calibration significantly. So we basically use the last 3 stages for our calculations. So instead of like one actuation, we have actuation of 3 stages. So that means the equation that here, A model should have like 3 terms coming from the 3 stages of actuation that we apply on this suspension. So now, initially we said that if we know how to move the mirror to a certain length, then we can calibrate the output photodetector fluctuations. But how do we move a mirror to a certain length? Then that's where this calibration process comes in. So in this case, there are many methods to actually calibrate that motion. But in LIGO, currently we are using what we call radiation pressure based calibration. We basically apply a small laser light at one of these mirrors. And we know that laser light exerts a force on an object, and that force is given by P over 2P over C. And if you know the force on an object, and if you know how the object will respond, then we can calculate how much the object will move. So this is the force, and this is the response of the mirror to a force, and which is basically a free mass because these are suspended object. It can be thought of as like a free mass. So free mass motion is given by 1 over m omega square. So from this you can calculate what is the motion of this test mass for a given laser of power P. The angle is fixed at which the angle at which we send the laser to the mirror. This is almost fixed. Mass of the mirror is also fixed. And the frequency is basically we can select what frequency we want to modulate this laser light. So this is in our hand, and m and theta are almost constant. So only if we know P, then we can calculate. We can calculate, or we will know what is the length motion of this mirror. That will also be the differential length motion between the 2 arms, because there is nothing moving here. Only there is a movement here. That translates into the differential motion of the 2 arms. that will produce the fluctuation at the output port. If we know how much we are moving here, then we can calibrate this output port fluctuation using that. So here we are using this external light to calculate this. We generally, the main issue here is that we need to know what is the exact power that is falling on the mirror. That will decide how exactly we can calculate this length fluctuation. If I take like a 1 watt laser and apply a frequency of this, modulate the laser light at 100 hertz on a 40 kilogram mass, which is the mass of the mirror at LIGO, this produces a length motion of this mirror at the level of 10 to the power minus 18 meter. It turns out that it is at the same level at which a gravitational wave, it is the same length fluctuation gravitational wave produces. So by using this mirror system, we can calibrate the gravitational wave signal in our, we can calibrate this gravitational wave detector for measuring a gravitational wave signal. As I mentioned, the calibration accuracy directly depends on the measurement of the laser power here in this equation. So this is another pictorial representation of how these things is done. So we have a transmitted model where the laser light is produced and the laser light is sent into the chamber, because chamber is in the vacuum. So we have a glass window through which the laser light goes in and it falls on the mirror and comes back, and there is a receiver model that captures the return light. By measuring the light here and here, we would be able to tell how much the laser light fell on that mirror. And using that, you can, using the equation in the previous slide, you would be able to calculate how much the mirror is moving. So based on that, one can calculate the sensing function and actuation function, the model for the C and A in the previous slides here. And here is the sensing function and actuation function. Sensing function is basically a low pass filter, means our gravitational detector can detect frequencies of gravitational signal if it is below some value, but at very high frequencies, their sensitivity to gravitational becomes reduces. So that's the low pass filter definition. At the actuation function, this is basically 1 over f square, or as I said, each in the simple case, one stage of suspension gives a suppression of like a function form of 1 over f square, and if there is a multiple stages, then 1 over f to the power 4, 1 over f to the power 6. That's what you are seeing, but you're also seeing some other shapes. It's not the straight line. These shapes comes from the exact how exactly this system operates. But if you go far away from these resonant frequencies, then they almost behave like a 1 over f square, 1 over f to the power 4, as we know for a simple suspension. So as I said, if you know the C model, if you know the sensing model, if you know the model for the actuation, and if you measure the error signal at the output port of the interferometer, and if you know the control signal that we are sending in to control the mirror, then we can calculate the gravitational strain. But in practice, what happens is that we calculate this model at one time, but the model can change. The model need not be same after that time. So we need to calculate how much the model is changing. There is a scale factor that we use. So this is the scale factor that tracks how much the model is changing over the time. And similarly, you need to know how much the actuation model is changing over the time. So these are the time-dependent factors that we have to calculate. So to calculate the time-dependent changing factors, we inject what we call calibration lines. So we inject the lines that will be continuously applied on the instrument when it is running. So by looking at the height of the lines and how the line is changing, we would be able to characterize what these quantities Kc of t and K of t, how these time-dependent factors for these different models. So that's why we do have many lines in the interferometer. So using these are the frequencies that we have used for those lines in the Hanford and Livingston during the past runs, and you can always see that those lines present in the data. So based on those measurements, you can calculate what is the calibration of the instrument at one time and also how it varies over time. So this is a nice calibration uncertainty budget over the entire run, and you can see that it's mostly like the magnitude fluctuation is at the level of 2 to 3%. We can calibrate the data at the level of 2 to 3% error in the magnitude, and the phase is like 2 to 3 degrees. This is after correcting for this time-dependent variation. So why do we need this precision of this calibration? This is because if you want to make, if you want to like do a better science, like if you want to estimate the parameters well, if you want to know, if you want to do cosmology, for example, measure the Hubble constant H0, for all these things, we need to have these calibration uncertainties at much lower value. Right now, we have 2 to 3%, but if you want to measure H0 by like 1%, then the calibration uncertainty also has to come down to this 1% level. And also, if you want to like look for deviation from general relativity, because all these waveforms are modeled using general relativity. But if there is a deviation, then if you want to look for those deviations, then we also have to have a very good precision of this data. So there are a couple of issues even in this calibration process, like how we do the calibration using photon calibrator. It's because like we are applying some laser light on the mirror, and that can produce like rotation instead of like just a translation. It can also produce rotation, which is unwanted. So that will affect how much the length changes. So we need to correct for that. So those correction happens here. And also the object, the test mass also as it deforms, even though it's like rigid glass up material, at some frequency they start to like deform at their natural resonant frequencies. So we also need to take into account when we apply an external force like this photon calibrator beam. So that also changes how the calibration can be done. So that has some effect on that estimation. We also use, and how do we do calibrate like a different instrument at the similar level? So for that, we basically have a common standard that goes between these different instruments. And so that we have a common standard to like calibrate this power of this laser, the auxiliary laser that we use for photon calibrator. And so LIGO India will also have something like common between these different sites. So this is what are the uncertainties currently in this process. So the total uncertainty is like 0.4% based on the photon calibrator. And in the past trend, it was like 0.64. Now it has become 0.39. There are also efforts to like see how we can do comparison between different institutions, because right now whatever I was discussing only between the LIGO sites, but when the other detectors come up, you also need to do cross correlations, cross calibration, and for that you need to understand how these different sites agree with each other. So this is as far as my effort to do that, comparing different sites. Okay, so this is the conclusion slide. So we had covered both the characterization of the detector characterization of the LIGO detectors, which is needed for identifying gravitational events, and also to improve the sensitivity and also the parameter estimation of those detected events. And also we looked at some aspect of calibration uncertainties, calibration in the LIGO detectors. Right now the calibrations are at the level of few %. But if you want to go much better, and if, for example, if you want to detect the measure the Hubble constant to good precision, then we need to go to the calibration uncertainty of like at the level of 1%. And this requires a lot of work. And that's what people are now looking into it. I think that's all I wanted to cover. If you want to look at some of these things more in detail, like how the analysis is done in the LIGO and also the LIGO data that you want to know, see, you can go to this gravitational wave openscience.org. There are workshop and tutorials that are available, and also data is also available. So you can go and look at them yourself. Thank you. I think we are at the end of the time, but I can take a few questions. Tanmay has this radiation pressure of high energy coherent laser mirror that could also mimic. So we are basically using this process of these properties of radiation pressure to actually move the mirror so that we can calibrate the mirror. So there we know how much the mirror is moving, so we can calibrate the mirror. That's the property we are actually using here to calibrate. So the other question, what type of laser is ideal for detecting gravitational waves and gravitational strain? So the detection, the main laser that we are using could be different. So when I'm talking about photon calibrator laser to use calibration, that need not be the same laser as the main laser. It could be a different laser, different wavelength. In our case, they are like differ by few nanometers. So the main laser is used 1060 and 1060, and the laser used for calibration is 1047. So they are different by 10, almost like a 10 nanometer. So the laser used for detecting gravitational signals, it depends on like what are the optical components that are available. Currently, the state-of-the-art optical components available for only infrared lasers. That's why we are using these infrared line our interferometers, and also the stability of the lasers. Right now, we don't have a laser that is very stable in the higher wavelength, lower wavelength region. In like visible light, we don't have very stable lasers at this point. So that's why we are also using infrared laser in our detector, because infrared laser is industry standard. So we have a lot of lasers that very good stability that we can get. But if we develop lasers with other frequencies with the same stability, then we might be able to use them in the instruments. But the lower the wavelength, I think the better for the sensitivity. But right now we are not able to produce lower wavelength, at least like visible length or even ultraviolet lasers are very stable amplitude and frequency. Okay, if there are there any other questions? I think we are almost at the end of our. I heard that there is also other sessions planned. Okay, if not, I will conclude the sessions today. And thank you everyone for listening.
Thanks, Shivaraj, and for the lecture. And I hope people had a good overview of how LIGO detectors are characterized. So with this, I'd like to thank Shivaraj, and this was the last academic lecture of the summer school. I thank all the participants also for sticking around, and now we have a special session for careers in astronomy and astrophysics. And the session would be led by the director of IUCAA, Professor Shivaraj, Professor Dhruva Saikia, and the summer school coordinators who is around. So, Professor Saikia, are you online?
Yeah, I'm there, Dipanjan. Yeah.
Okay. So I think the plan is we will let you and Shomak to sort of conduct the session. I have asked Samir to prepare a couple of slides just to give a few point-wise information to the students about what are the various opportunities available, etc., and so that they have a guideline. And then you and Shomak can take on, give them a broad overview of, the question should we focus on for a career in astronomy. I think this was a common theme on many of the participants who were asking us. And I'm sure other participants will also have some questions, which we will try to answer to the best of our abilities. So I'll let Shomak and Sykes to sort of take over.
Thank you. Thanks. Thank you, Dipanjan. I hope people can hear me. It's great to be back with this bunch of people who have been with us for more than a month now. And I'm very happy to see that so many people have stuck with us till the end, which just shows the resilience of not just the people who are attending, but also of the material that has been presented. I can think of many other subjects in which you start off such a very intensive session, and then about 3% of the people are left at the end. So I'm glad everybody's here. I hope you've enjoyed the whole summer school. Again, we enjoy this much more when we are together in person. And then people can, after the lectures, sit with a cup of tea and talk in person. Our summer schools are quite well known for their parties and food and things like that. And these things are difficult to do. I'm sure in a few years people will figure out how to do parties on Zoom, but certainly we haven't figured that out yet. In fact, I've been to some conferences over the last year in which we try to simulate that. There are people who send Swiggy to certain places so that people get some food, or they bring the same menu. We have a published menu. Everybody cooks the same food and eat together and things like that. A lot of that is great fun. But at least in this particular setting, we have had a wonderful menu of astronomy, let aside food. And just looking at and I've attended quite a lot of these lectures. I'm sure Professor Saikia has attended a lot. And just to see the menu that has been offered to you, I hope you found it. I already see in the chat box people saying that they have liked the material presented to you, and so I hope this has given an overview. The whole point is to give an overview of the subject. The subject is very vast and very fast evolving, and one of the major problems with the subject right now, I wouldn't call it a problem. It's what keeps us in business, and that is that it is fast evolving. So things don't get into textbooks. You can't find a textbook that will tell you what we have presented to you. And to me, it is the best time to be in a subject. Because if you think about the beginning of the 20th century and the electron has just been discovered and people are discovering what's inside the atom, and then in parallel, quantum mechanics is being developed. And in parallel, Einstein is putting together his theory of relativity and general theory of relativity. All that was happening within 10, 15, 20 years, right? And think of being somebody who's a student of physics in 1905 or 1910, and all this is happening. Similarly, I think a student of astronomy now is facing an explosion of information in terms of all these things that are coming through. You just heard gravitational waves, and then electromagnetic waves in X-rays, in gamma rays, in radio, in optical, and that is driving the subject. Astronomy is a data-driven subject. It is not a subject in which somebody sits and does some calculations and then waits for some experiment to happen. This is where we learn things from observations. We find amazing objects and then we try to explain them, and thus the subject evolves. And so I think that flavor I hope you have got right now. And so this is just sets the stage of how fast the subject is evolving. You don't get things in textbooks. And this also means that if some of you, and I know there are two classes of people here. There are people who are teachers and there are people who are students who both came together to attend this set of lectures. And for teachers also, this is a place where you might be a teacher of some other specialization within physics, and you're coming in and learning about the basics of what's happening in this subject. This just provides a way of coming together and learning about the exciting things in the subject. And then you decide whether you want to take this up for a long-term pursuing of research in the field, or even if you're on the sidelines looking at what's happening in the subject and dipping your feet in the water, as it were, then even then that this provides you a background of what's happening. So I think, and this also tells you that this is a very exciting time to be in there. So part of the reason of having a session, a final session like this, is also to look at the career prospects of people, of how you get into a subject, this subject, if you are an undergraduate right now or a slightly more advanced student, how to get into research, and we'll discuss all that right now. But before we get on to that, I just want to invite Professor Saikia to see what insight he's had into attending all these things and interacting with you a little more than I have, and what his feelings are at the end of this, another of these long sessions that he has amazingly organized on our behalf.
Okay, thanks very much, Shomak. Thanks a lot, Dipanjan and Samir, who are here as well and have taken a very active role, and led by Dipanjan, we have all sort of tried to interact with you as much as possible. And as just Shomak pointed out, that for students as well as teachers, it's one of the very exciting times to be doing astronomy. Even in India, you can see exciting results coming out of AstroSat, UGMRT, the upgraded GMRT, which is much more sensitive and has a much wider frequency coverage than earlier. And all the projects that India is playing a key role in, whether it be the Square Kilometer Array, whether it be the TMT, the 30-meter telescope, LIGO India, the South African Large Telescope, which are all opportunities available to the coming generations of students as well as faculty members. So it's a very exciting time to be in. And this year we also, as you noticed, that we also tried to put in a bit of an experimental component in the program, which was challenging, but it was very useful as well. And it was wonderful when some of the teachers said they are going to implement some of these in doing some of these experiments with their students, because that is a larger intention, that if more of you take it up and propagate it further, and we will try to build on that, things which you could do with equipment which is easily available to you at your home. I don't know how long the pandemic will continue. We have to be safe. And although things are coming down, we don't know how we are going to react to the different mutations or variants that might come up. So while trying to be as safe as possible, we also want to try and bring home the excitement of astronomy, the excitement of science. And it has been wonderful interacting with you all. You all have posted questions, you all have taken part in the chat, and the attendance also has been very good all throughout. And Dipanjan and his colleagues and all of us have put in a lot of effort behind the scenes to make sure that everything goes smoothly. So I hope it has been a very enriching experience, as it has been for us. We have really enjoyed being able to interact with you all, and it's been another sort of very, very interesting and enriching experience for us. So now I think we'll probably go to Sameer's slides, and then we will take on questions.
Yeah, before that, I also wanted to add my admiration and thanks to the people who helped organize this. I mean, there's a large team of people, and I probably should not mention every name because, of course, I'll leave out a few things, but you know who you are. Dipanjan Mukherjee has really put in his all behind this time. And Professor Surud More and Nishan Singh, who organized last year's workshop, have also actually participated in a huge way in getting this all together. And the entire TLC team that works with Professor IUCAA has also helped. So very, very nicely, this has been done. This year, we had the largest number of participants. So that was a big challenge. And, people who have attended the exams, etc., also have, there are challenging ways of doing things. So we'll come back to some of these issues later on. And Sameer, thank you very much for your contribution to this organizing this, and the people who have looked at the YouTube presentations, the recordings that are kept everywhere. Santosh Jagre, who's actually worked very hard in putting the databases together, and the PV works and stuff like that. So let me pass this on to Sameer to initiate the discussion on careers. Dipanjan, did you want to say anything before he does that?
No, I think you and Sais have completely covered everything. It was a joy and a pleasure to sort of bring the research and the work that we're working on in astronomy to the undergraduate, the future astronomers, let's say, hopefully. And it's always very interesting and nice to interact with young students and also senior teachers as well who have joined us with the refresher course, to help us sort of understand how we can also take this interaction sessions in different directions and improve the flavors. And finally, I also want to thank, again, Santosh Jagre hasn't mentioned. So Santosh, Sagar Bhosle, and Yogesh Thakre, they have been working nonstop till late hours, I can confirm that, so that everything has been running smoothly. And I really am thankful for them for making all of this happen without much more intervention from us. They have actually worked a lot more than what we have worked on. So thank you, everybody, for making this.
battery. Fuji.
So there's somebody who's just okay. I'll let Sameer sort of take over now, and then introduce a few slides, giving us a list of information for how we can, those young students and people can have an approach their search for career in astronomy, and then I'll let Shomak and Sykes to take over with the question answers. Sameer, please go on.
Thank you so much.
After Sameer puts up the slides, you can raise your hands to ask a question, or you can put it in the chat box as well.
Sure.
Go ahead, Sameer.
Good to, yeah, thank you to all the to Dipanjan, my friends, other friends, and my senior colleagues here. This is a very important responsibility that has been given to me to summarize. Let me just share my screen to summarize some ideas for aspiring astronomers who are there in this this group here. Also, of course, there are educators who have attended this as a refresher, so they may also pass on some of these tips to their students. I also hope I can do justice to this so that I can get a free coffee after this session. So I think this particular set of slides, it won't be a couple, but a few slides would be more useful for the people who are right now at the postgraduate level. These things mean different in different countries. So just let's go along in a general way. And the next step would be a doctorate and then do research in this particular subject. This particular screenshot is from a popular poster that we usually show on our National Science Day here. And this basically shows that you need to be a science student or an engineering student, and you can easily get into astronomy. So it's not just physics that you need to know. You could also be a student of chemistry, mathematics, biology, have computers, interest in computers, or be studying mechanical, electronics, or electrical engineering. And there are many other things which are left out of here. So there are various ways in which you can contribute to astronomy, and whether you are a science student or an engineering student, although you need to know physics quite clearly, you can still have other skills and be part of astronomy. So that being said, let me just quickly get to a few general suggestions, which I'm sure people would be giving here and in other sessions. This is kind of a few steps that we recommend to UG PG students. They should first work on, in these 3 or 5 years that you have, you should work on your concepts of science of physics that you're studying, of the post-graduate subjects that you're studying, and also look at their applications. So if you have a good understanding of that, then I think your path becomes much easier in the future. Then you should try to gather some skills in coding and software. You've seen the importance of that during this summer school, I'm sure. A few things that we suggest are looking for internships and winter summer schools, like you've already probably done that here, but there might be others, and there might be short-term ones. Many universities, institutes, not just in India, but also abroad, they give chances for, say, not month-long, but sometimes a week-long internship even. So try to get as much experience as possible from these short-term interactions with scientists. You could also do a project. So if you're in first year or second year, so you could volunteer to do a project with a scientist. Just ask them if they have something to give you, some task to give you, which you could implement for them. This will just may not give you a lot of knowledge about the in-depth astronomy, but it will give you a idea of how a scientific method works. In your final year, whatever, if you're in BSc or MSc, try to do a project, the final year project with a research institute. And that is one of the ways in which you will really get to connect with research level work at an early stage. Of course, you should then approach your PG level exams where you have to give entrances and then qualify for PhD programs. You should apply for Indian and foreign universities and join for those topics, join the best places for the topics that excite you. That's very important, because if you just go for something that just comes your way, maybe you'll not feel so satisfied after a little while. So of course, I'm not giving too much opinion here because the seniors will advise you better. This is one of the things, few of the things that I put as general suggestions. Now, what are these topics which might excite you? So in general, I have tried to put together a few of the things, subtopics of astronomy that are talked about. Things like theoretical and observational astronomy, which has this bifurcation is there, and you could be studying galactic astronomy or extragalactic or relativistic astrophysics. Gravitational waves is a very popular subject these days. Cosmology, IUCAA is quite famous for that. Then you could also be doing observations of, there could be fields like solar physics, which have both observational and theoretical aspects. So it's not, it was not an easy task to classify these. There could be interdisciplinary topics like planetary geology or astrobiology, exobiology, right? Which basically are crossovers, and you're still doing some astronomy, you're still contributing to astronomical knowledge. and also bringing in your own field skills that you may have from your UGPG. So these are some of the subfields and related fields of astronomy that you can get into. So I think we'll be sharing some part of these slides with you. So these are just examples of a few good internships, summer schools, winter schools that are there. So VSRP is a very good program which runs at IUCAA, at NCRA also across the road. Just as an example, ISSAA have also started coming out with their own summer programs. So you should look at those. Then there are other programs in other countries. They could be by some institutes, by some universities, by even some projects like LIGO, where you can get some good fellowships or some good experience even during your undergraduate phase. You should, after that, of course, as I said, make a list of all the PG entrance exams that you want to give. So this is just a few of them noted here, including the INAT, IUCAA, and CRA admission test, JEST, which are the two, the joint admission test. These are the few ones which you have to give to get into good research institutes in India. But of course, you should also try abroad and not lose out on any chance that you get after your PG. Here are a few resources. Again, this is a big list, but a few of them will allow you to, despite not being in an astronomy course, let's say most universities in India do not have a BSc or MSc in astronomy. We don't even recommend having such a course right away at graduation level, because there's a lot of physics to be learned before you are able to grasp some ideas in some concepts in astronomy. But then even during that, there are many online courses, etc., which are available, including the Swayam courses made by the IUCAA Astronomy Center for Educators. But there are many others which you should look at. There are also very fun things to look at, like minute physics, etc., which will kind of keep the excitement about astronomy alive in you, other than your coursework. There are good blogs which keep telling you about internships and programs outside India. So you should bookmark these blogs. I think blogs like How to Make an Astrophysicist, run by Hana. Astro Better is another very good blog. Internshala is an Indian blog site where you get ideas about internships, not just in astrophysics, but across things. So the AAS job register is something you will later require after you, let's say, get into PhD or afterwards, which therefore I've included at the end. That is when you will get into an actual career in astronomy. So this is one of the very important sites which people consult when they need a job. They are looking for jobs in astronomy. So what are these kind of career positions which might be there? Again, it's not a comprehensive list or anything which is a holy grail, but you could have career progressions, like you could probably join somewhere as a scientific trainee, project student, project assistant. These are the beginning phases, and then you could go on to become scientists, experimental, theoretical, or teaching faculty somewhere, or you could run an observatory somewhere. Other than that, of course, given your skills, if you're an engineer, you could even, or a computer scientist, you could even become a data scientist working in astronomy. You could be scientific technical officer working at astronomy institutes. You could be a science systems engineer or a software developer even for astronomy. And all these, I've seen all these positions having a lot of weight in the upcoming mega projects, especially in which all sorts of skills are needed, because these are new facilities which are being created, and every kind of skill is very important for them. Of course, other than these, also something which is close to my heart, you could do things like outreach. You could be educators and for astronomy. You could be in public relations. You could be technical writers. You could be technician, etc. Even aside from all this, you could even be an amateur keep being an amateur astronomer and do some other job. Or you could take up designing or become an artist who does really great work with actual data or actual facts in relation to astronomy. So these are, of course, just sidelines that I also like to do. So with that, I'll conclude this quick set of slides and wish you all the best from all of us here at the IUCAA SciPop. You are welcome to contact us, and of course now I think you'll get a lot of better advice from Professor Shomak Chaudhary and Professor Dhruva Saikia. Thank you.
Thanks very much, Sunil. Thank you. That was great. That was a wonderful summary. And we'll talk about specific topics in a minute. But let me just give an answer to the number, which I think should answer a large number of questions that we are receiving offline and online in the chat box. And I've received a lot of emails in the last few weeks about this. And that is, many people say, can I do a project at IUCAA right now, or in the summer, or in internship, etc. Now, there is no easy answer to that. And that is because in IUCAA, we have about 20 faculty and about 30 or so postdocs who can do projects with people. And each of them have received hundreds of such requests. We, in addition to this summer school, used to have something called the Vacation Students Program, in which 10 or 15 people come every year, and then they do a summer-long project. We tried to do this online last year, and our experience has not been very good. That in the level of interaction that people have had with us online, we could not get much done. And as a result, this year, we had a long discussion amongst our faculty about how we should manage it this year. And this year, we found that the people who are eligible to do such projects with people said that they don't think this will be possible. You can't really do something substantial without a very intense interaction over a month or a week or something like that. Now, I know that that is a disappointment to many people, but I will tell you, and Professor Saikia might tell you this, we had a discussion about just this problem with a much wider audience. And that is, IUCAA has about 180 or so associates who are teachers at Indian universities, a lot of universities and colleges. And actually, some of them are here on this call. I can see them who are attending the refresher course. Now, and we have had several discussions in which we are thinking of how to bring together a bunch of projects that people can do with IUCAA members and their associates together as a resource pool. So because it's all online now, and I don't think you will be able to travel to some laboratory or department and stay there for 3 or 4 months and do a project right now. This is not going to happen this year. And so we are just trying to get together a bunch of people who will be willing to do this. They will not necessarily be at IUCAA. They could be at Delhi University or Tezpur University or at Cochin or Kashmir. But it doesn't matter on Zoom, right? So, but these are people who are willing actually to take students through a project online, because many people are willing to do that. People think Zoom doesn't give you the right way of interacting on these research projects for people who are undergraduate or postgraduate students who have not had enough to learn before doing research. So these things are continuing, and please keep your we will announce such things in which we will have a collection of various projects gotten together from people who. And so then this question, can I do a project at IUCAA, is going to be transformed into, can I do a project with anybody on Zoom, which would be worthwhile, which can be organized by people at IUCAA, I think is more relevant now. And this will happen. So I think today, let me just give you that information, and I see whether Professor Saikia has anything to add to this. And we'll see. We don't have an ready answer for you right now, but we hope we will very soon. Sykes, do you want to say something?
Yeah, I think you've covered all the essential aspects, Shoma. And all I would say is that there are challenges in trying to do things online. It may not be perfect, but it can still work. And for those who are willing, we will do our best to sort of facilitate that, as Shomaka just mentioned. I mean, for example, I'm now working with two of the MSc students of Pune University. It started off with their MSc project, but they want to continue working on the project for the rest of the year and hopefully write up a small report or a paper on it. So it is obviously not as good as sitting across the table and having a cup of tea and discussing. But on the other hand, we can't also just completely put our hands up and say we can't do anything.
Yeah, absolutely. Absolutely.
So we have to do the best we can under the circumstances. And in many cases, it can work. In some cases, it may not work. So we will continue to endeavor to do our best. Okay? And keep an eye on our website, because whatever is possible, we can email as well as put it in our web pages so that you're aware of it. Shomak, on this theme, there was also a question in this chat saying, can one pursue PhD here at IUCAA in spite of pursuing their masters in foreign countries? Do you want to just briefly address that?
Yes. So let me address that. Absolutely. I mean, we've had many such cases. This year is an exception because of the logistics problems, and I'll talk about that soon. Because right now, in fact, starting now, in 1 minute ago, is the meeting that has started of the JEST committee all over India to decide whether JEST will be held this year. And maybe within half an hour, we will not get an answer. But anyway, so we'll talk about those things later. So just this particular thing about whether we have a PhD anywhere in the world, or master's anywhere in the world, or an undergraduate degree anywhere in the world, doing a PhD in IUCAA is absolutely possible. I mean, our PhD program, the entrance to our PhD program comes from certain undergraduate backgrounds. And by undergraduate, all over the world, by undergraduate, people mean a 4-year post-class 12 degree. In India, it is 3+2, which is soon going to be the same according to the new education policy. But right now, what we do here in IUCAA is, if you have completed an undergraduate degree, we still ask you to appear at one of the national exams that was talked about. There's a JEST exam, which is for all physics institutions in the country. And then IUCAA has its own entrance exam called INAT, the IUCAA National Admission Test. And typically JEST is held, now this is very unusual year, JEST is held in February, March, INAT is held in November, December. And then there is the NET exam, which is held by UGC and CSR and things like that. And so we have certain criteria for people who get a certain amount of marks in the JEST exam or in the INAT exam or in the NET exam, etc. And then we interview them, right? So our entrance, PhD entrance, depends on that interview. And the interview happens, now it is happening online, happens with 2 interview committees interviewing each person. Sometimes it's even 3. And so it's a pretty rigorous interview process. But where people come from for that interview can be from a variety of sources. As I said, it can be from the NET, it can be from the JEST, and this year we don't know whether JEST will happen. It can be from INAT. Last year we did not do INAT. And so this is a tough time. But this can also happen if you have a strong undergraduate degree or master's degree from abroad, and you could sit for any of these exams, right? Now, in the past, we have had our exam actually held in some foreign countries. Iran, we used to have a bunch of students from Iran. There was a point when in Tehran, we had a center and things like that. And in certain cases, we've had these exams held in some university. The problem is that you'll have to come through these. And so, for example, if you have had an undergraduate degree in some other country, but a master's degree in some other country, but you can sit for this exam, then it's absolutely all right. The other way one can do, but the problem is that we can't take you straight from having a degree at a foreign university. You have to be eligible for these interviews. Another way this has happened is that with certain foreign universities, we have an understanding that they they can recruit the student in that university, and they do their PhD here. Very recently, we've had one such example in which we have a British student who's doing a PhD in IUCAA, but he's a student of Southampton University, which recruited them there, right? So it's a kind of joint thing. So that's a very long answer to a short question. If you have a specific question in mind, like I did my master's here, and I'm now sitting abroad somewhere, or I am in India now, what do I do? Then we can answer questions like that offline. You don't have to do it in this forum. But the general way of doing this is follows. We have entrance exams, and you have to qualify through the entrance exams. And then we have the interviews. And it doesn't matter where you've done the undergraduate degree to actually sit for these entrance exams. I hope I've covered everything.
Thank you. I think you've covered everything. I've been just answering some of the questions in the chat, but maybe a lot of hands are up. Maybe we will try and look at that. And okay. Anushka Tillikar, you want to unmute yourself and ask your question?
Yes. Hello, sir. Am I audible?
Yes.
Yeah, you're audible.
Okay, so I have two questions. First being that when in the slides, sir mentioned that one should have good coding skills for a better career. But I want to know that apart from Python, which other languages one should know clearly in order to work effectively on the projects. And the second question is that when you receive a lot of emails from students like us about asking for project positions or assistantship positions or anything like that, what exactly you look in the profile? I mean, what we should have in a profile to make it effective or greatly eligible, outstanding than other applications for that particular position or any research position or project position?
Okay. Samir, you want to mention about the coding thing which you mentioned? You want to elaborate on it further? Samir, you're there?
Thanks. Just to also let you know, Surud is also here. So
okay.
Let's
okay.
handle that question. If Samir is not available.
Okay.
There, sorry, I was away.
Yeah.
Surud, would you like to come in?
Surud, are you there?
Yeah, I'm here. Can you hear me?
Yes.
Hi, Surud.
Yeah, hi. So that's a great question about coding experience and so on, right? Whether you need to know particular languages, etc. So I think my answer would be, and maybe some of the panelists here, if they disagree, they can say these things. Coding is a skill, right? So once you know one particular language, then you can pick up any other languages which are required, right? So it's not like, okay, you need to know this specific language and this specific language, etc. Programming is a skill by itself, right? If you know Python, or if you know any other programming language, say C, C++, etc., you can pick up the other languages as and when required. So that's what happened with me, basically. Like personally, I only learned one language in a class, but then afterwards it was just picking up as and when things were required. And this particular process is like an ongoing process, right? So when I started, there was not much of Python there. So we started with Fortran, but then as times progress, then you start to pick up these other languages and skills, right? So, but what is important is to understand, right, how to get things done with a computer. Right, and if you have a task at hand, sometimes if you can think about it, like oftentimes what happens is, once you know many computational languages, is given the task at hand, you have to ask the question, okay, which language can I use in order to get this task done the fastest, right? It involves both like writing the code and then running it as well, right? So oftentimes it's mix and match for me these days, right? But even if you know one of these languages, I think that would be good enough. And then you will have to pick up. So in astronomy, one thing that I've learned, the best quality that is to have like a quick learning curve, right? So if you can learn things, then you can make a lot of progress, right? So there are many aspects which come up one after the other, many new things. We are always at the forefront of research and things that can be done, right? And so that sometimes requires you to be very flexible and adaptable. So if you have those skills, then that helps.
Okay.
Yeah, and you had also asked this question about what we look for in applications.
Yes.
Yeah, so
that's because in the recent months, when I applied for a few project positions in some foreign universities, what they mentioned was my profile was very strong and good. But what happened was the other applications which were there, I was the only one who was at the bachelor's level, and the others were of PhD and master's level. So they mentioned that although your profile is better than theirs, they have experience which you don't, so we will go with them, although we will still look up for your profile a few years after.
Yeah. So these kind of issues are quite possible, especially when you're applying at foreign universities. They don't get a direct time with you, right? So in IUCAA we do interviews. Can you please mute?
Sorry for the disturbance.
No problem. So in IUCAA, for example, we do in-person interviews often, right? At least in pre-pandemic times. And so it is then easier to gauge the level of an applicant. In foreign countries, often they have to just go by the paperwork that has been submitted, right? And so these kind of barriers are there. So I would definitely encourage you to apply for any of these internship positions. There are multiple institutes which have vacation programs. So you can apply to them, and then you can gain some more project experience along with them. In addition to these things, there are also many citizen science projects which involve astronomy, which are being conducted. And so if you get involved with them, you can not only get involved with them in order to do the work that ordinary citizens do, but you can also download that data and try to play around with it. And there are discussion forums on these citizen science websites, which may help you to connect to some of these researchers. So if you're interested in getting to do more of the science part from the citizen science, then those kind of avenues are also open, right? So these kind of things will help you to build some sort of a project profile, or some sort of a profile which will then help you in getting other positions, right? And of course, when we get applications for project positions, we do look at whether, so for example, especially for me, who has to do a lot of heavy computing, I would look out for people who have some programming experience, right? Otherwise, you would spend the whole month just learning that particular programming language rather than actually doing the science, right? So these kind of issues are at play. Sometimes, of course, it is also whether we have enough time to spend in order to get you to a particular stage, right? To get the project done. So there are multiple issues and aspects which go into these decisions about selection of students. I hope that helps.
Okay. Yes. Thank you.
We have lots of hands up, but I would like to add one thing to what Sudhir said, which might address a lot of the concerns that are being expressed here. When you go through the Indian education system, you often don't realize that we have a pretty complicated system compared to what other people have elsewhere. And when you're applying abroad, they're looking at the Indian system as something that is not quite the same as theirs. This is because we have the 3-year bachelors. And after the 3-year bachelors, a lot of people think that they are eligible to go abroad to do PhD programs, because In other countries, people go into PhD directly from the bachelor's. There is no master's program like we have in India. You have to understand that. Our master's program is an essential part of our education before going into a PhD. Nowhere else in the world is a master's program an essential part of the transition from undergraduate work to graduate work. A master's program exists in Europe and America only as a terminal program, or it is used if you want to switch one subject to another. People go from a bachelor's program to or an undergraduate program, which can give you a master's M something degree, but it's an integrated program. You don't have to do another degree, and then you go to a PhD program, right? This is everywhere. And when you apply after your 3-year bachelor's in India, nowhere else is there a 3-year bachelor's program that feeds into a graduate program. Then people say you're underprepared. So when people come to me to ask, and a few years ago, I was one of those people in a university abroad in charge of graduate admission, and I would get hundreds of letters there, not sitting in India, but sitting somewhere abroad. Same thing would happen. And I would always give the advice that if you really want to go abroad to do a PhD, first of all, you don't need to, because there are lots of PhD opportunities within India. But if you do want to go abroad, think of going after your master's, not after your bachelor's. Because we are not prepared after our bachelor's to go and face the challenges of an American or a European PhD program. There are certain 2-year master's programs that are available in Europe now, not in England and not in the US. In Europe, there are certain countries like in Germany, like in France, like in Switzerland in particular, who offer English-speaking students a 2-year program. Those are very good. They're not often funded. So it would be, you have to get an independent scholarship for that. Otherwise, do your master's here. The Indian master's programs are much, much, much better. And remember, you have to do a 2-year master's after the 3-year bachelor's that we do. If you've gone through the university system. If you've gone through the IIT system, again, or ISSAA system, you have the integrated program, master's program. Those are very, very essential, right? I hope that answers Anushka's issue. People who have dealt with Indian students do not trust the bachelor's system in this country in order for them to get into research. You have to do a lot more to get into such a program. Sorry, I just wanted to say that.
Okay.
There are quite a few hands up, so we'll move rapidly. But before taking up the next one, I'll just quickly answer 1 or 2 questions in the chat. There was Shreya Sigatia who asked about study material, particularly for appearing in the entrance examinations or interviews in research institutes. So what I would say is that, many of us have gone through that process, and what is expected is that whatever you have studied in your undergraduate or postgraduate studies, you know it well. The interviews or tests are not to psych you, but to just understand how well you know your basics. Because once your basics are clear, you can build upon that. So it's to sense your enthusiasm and to just see what you're supposed to know, how well do you know it. So there are no Agarwal sort of classes or kind of thing that will help you. It is just what you regularly learn in your MSc or BSc, that you learn it well and do it well. Then Meghna Pillai, she asked about writing to faculty members about projects and all that. You're welcome to do that. You're definitely most welcome to do that. But as you can see that we get inundated with applications, but that doesn't debar you from writing. You're most welcome to write, highlighting your strong points and why you wish to work with the person. Okay, there's just 2 quick responses, and then we'll go up to Junik Sengupta. Junik, you can unmute yourself and ask your question.
Hello, sir. Am I audible?
Yeah, you're audible.
Okay, sir. Thank you. First of all, it was a very fantastic session. This 1 month has been the very best month for last few years for my life. And sir, my question was, could you please refer to some online libraries where we can download or borrow books for some time? Because most of the time when we are trying to get some book, a few of them which are a few very high cost as come to buy them, and we are trying to download the PDF. Most of the time, they are not available. So, is there any way we can do it from any online libraries out there?
Sorry, actually, I missed your question. The voice
Well, Unique wants to know where he can download books online, legally or illegally. I can't tell you illegally downloading books online. It depends entirely on your Google skills. How can I recommend something like that in a session that is being recorded? But people who know where to look, they know where to find PDF copies of standard textbooks. Otherwise, what will happen is that if you are part of a university, they will have ebooks in the library of everything, right? That you need. If you don't, then you ask your university or college to get ebook versions of some of those books, and then you can get them, right? Otherwise, I don't think we can answer your question.
Okay, we'll move on to Neil Vadoria. Will you unmute yourself and ask your question?
Hello, sir.
Nick, you can lower your hand so that we know that your question has been answered. Neil, would you unmute yourself?
Yes, sir. Am I audible?
Yeah, audible, yeah.
So my question is, now I'm a master's student in my second year, and I'm interested in pursuing astrophysics or cosmology as a PhD and research topic. However, I'm not very sure about what in astronomy or cosmology I would like to do. And I always get a conflicting advice where some people say that it's only after you join a PhD program you would get to know what you want to do. And I also get an advice that you should go to places where there are professors who are doing work in the fields that you are interested. So what would be the correct approach to it? Should I just go for look for programs that are offer me a doctorate in astrophysics, or should I actually go for a particular problem at this level and find out who are working with that problem?
See, it depends on you to a large extent. I mean, if you're quite clear about the area that you're working in, now you mentioned about cosmology, then you should try for a place which has a good cosmology group. But usually what happens with most research students is that the specific problem that you work in a larger field, develops as you know a little deeper of the subject, a little bit more about the subject. So it's often helpful. I mean, once you know the broad area, you need to narrow down to the specific problem that you're working in. So it's good to go to a group where there is an active group on the broad area that you're interested in, but then you can focus later on the particular problem that you want to work in, because that also evolves as you develop a deeper understanding of the field. Often, I mean, that has happened to many of us. Okay, so would anybody else like to add to that? Dipanjan, Shomak?
No, I think this question is very valid, and this is something that we have all gone through at our early stages as well. And there is no easy answer to this, to be honest. The thing is, what I personally found when I was looking for what to work on, everything was interesting. But the thing is, you start working on something, and as you delve into the topic a bit, your expertise or your understanding and experience also broadens slowly. It's a very slow process. So it's good to start doing projects at an early stage. That's what I would say. And this gives you helps you broaden your horizon, and then you can find some depth and understanding. Okay, I like this topic. I am personally interested in this, and then you can go forward. So if you do projects at different places and start learning about the subject a bit more, from bachelor's and master's, you can start doing projects on that subject. You can find what interests you more, and then slowly find a particular niche area after in that where you think that you will be interested to pursue further. Shoma, would you like to add on this?
Yes, very briefly. See, we all have our own experiences, same thing. And Neil, I've talked to you before about this as well. It is very hard to know. It is like going to a bookshop for a book. Unless you actually browse through the books, you don't know which one you like. For example, I went to Cambridge thinking that I'll work on pulsars. I ended up working on galaxy dynamics. So, and that is because I shopped around after I started working on pulsars, I thought I would do something else, and I had somebody else, etc., etc. And finally, so it is worth going to a place where you have choices. The problem is that if you, for example, want to work on pulsars, but you go there and find that you don't like pulsars, you've gone to a place where there's only one person who works on pulsars and nobody else works on anything else, then it is a difficult situation. So it is a good thing to, if you have the choice, to go to a place where you have as wide a menu as possible. Then comes the divide between the three aspects of astronomy: theory, observation, and computation. For example, if you're completely interested in computation and simulation and maybe big data, AI, that kind of stuff, then if you go to a department where there is no computer, a big computer, and only a bunch of theorists sitting around, then you won't have those resources. So that is the thing to focus upon. To focus, for example, if you want to do, actually you like the romance of working with telescopes at night, then don't go to a place where there is no night activity. There is only a bunch of people working with pencils. So you should choose a place which has an access to large telescopes, has access to space-based observatories and things like that. So you can concentrate on the resources and concentrate on the variety of subjects, right? And so if you want to work on extra astronomy, don't go to a radio astronomy department, things like that. Once you do that, then I think it would be, because that's what research is about. I mean, you should know what you want to do a research on, right? If you knew the answer, then what's the point in doing research? So the excitement of the subject should drive you. Keep your options open. I think that's what we are saying.
Thank you, sir.
Shomak. So we'll move on to the next person up, Ayush Garg. You want to unmute yourself? Neil, could you lower your hand, please, so that we know your question has been addressed?
Hello, am I audible?
Ayush, you're audible, yeah.
Hello, sir. First of all, it was very wonderful experience to have such a great knowledge in this past month. Being a mechanical engineering background, it was not that easy to gain such a deep knowledge in astronomy and astrophysics. My question is, I'm a BTech mechanical and I have cleared JRF in physics as well. But the thing is, after struggling for many years, I haven't found a platform where I could find a research program or if I could apply for PhD. There are often chances where I get to know that I need to pursue masters first in order to have a career in astrophysics. But the thing is, I'm not such from a sound financial background. So I need to know if it is like I saw on the IUCAA website that using JRF, BTech students can apply. But after following for a complete year, I haven't found an application form, any advertisement regarding that. So I wish to know if I could apply for astrophysics over here or for any such program, and how could I do?
Shomak, you want to take that?
Yeah, so I could hear you very well, but are you saying that you didn't find application forms for any program or any particular program you're talking about?
Sir, I was searching for astroparticle physics.
So yeah, the thing what you call astroparticle physics might be called something else somewhere else, right? What do you mean by astroparticle physics? Astroparticle physics, often people who search for dark matter particles, they call themselves astroparticle physics. People who do neutrino astronomy, you can call that astroparticle physics. You're looking at the interface of particle physics and astrophysics. That's it. So some people actually have called their department the Center for Astroparticle Physics. You know, there is a whole Center for Astroparticle Physics in Nordita, and there is a Center for Astroparticle Physics in Boulder, Colorado, and that kind of stuff. So, but you will find that a lot of the astronomers who work at the interface of astronomy and particle physics are actually working in astroparticle physics. So, you know, if you are doing searches on a particular name that you think, rather you think about the subject and what you want to do. If you really want to work on dark matter particles, or looking for neutrinos, or something like that, then you search for such programs. Okay, there, for example, there could be some people who are thinking of, the discoveries that are coming out of CERN at the high end of new particles, the Higgs particle, the new particles that are, what kind of application they have in astronomy. Then you can see that CERN itself has a huge astronomy group which works on such things. That is I think the reason you can't find astroparticle physics anywhere is that none of the Indian universities or departments have a center for astroparticle physics. We don't call ourselves astroparticle physicists, but half the work I do or Dipanjan does is actually astroparticle physics, right? So I think it's worth looking at what you're thinking about. If you're thinking about the astronomical applications of particles or particle physics, then there are many of us around. Many of
Sir, I had some topics in my mind related to astroparticle physics that I particularly interested in. Their cosmic waves, they're from gamma rays to ultraviolet rays that interests me a lot, and I wish to research on that particular topic.
Look at such things. Look at people who do gamma ray astronomy. Suddenly, you will start finding people who are working on gamma ray observing on blazars. Many people all over India are working on blazars, gamma ray variability of blazars, gamma ray variability of quasars. People who work on gamma ray bursts, who worked on Compton, who worked on the new gamma ray satellites and stuff like that. You can call that astroparticle physics, right? And that's what you mean probably. But if you can't find them if you search for a department of astroparticle physics. So look for gamma ray astronomy.
Is there any way where I could apply from just from BTech Mechanical Engineering to further integrated PhD or PhD, or is it must to have a master's degree?
No. For example, I'll give an example. There are gamma ray arrays that are being built now in Ladakh by the Bhabha Atomic Research Institute. Right? Huge arrays have been set up to detect gamma rays from astrophysical sources. Okay. The entire people who have built this, half of them are mechanical engineers. Right? And you're looking at you have to build a telescope to do this. Mechanical engineers are some of our. I mean, we in our labs here, we are now about L1 instrument that's going to look at cosmic rays from the sun. So you just have to find the right thing for yourself. I mean, in the first slide Samir showed that equal numbers of scientists and engineers work in astronomy, and some of the engineers actually do. Not engineering related things. If you look at Tarun Soradip, for example, who did the cosmic ray microwave background at IUCAA, he came from a mechanical engineering background in IIT Delhi. But he chose to do cosmic microwave background. But then you have Professor Ram Prakash here in IUCAA, who's an IIT Madras electrical engineer, who actually is building instruments for the biggest telescopes in the world. And so doing his electrical engineering in astronomy. So you can do both. You can actually switch your subject and do something else, or you can look for mechanical engineering applications in astronomy, astrophysics. You can do both. So do particle physics experiment, astroparticle physics experiment. There are people who are building instruments, right? And so they will need all kinds of engineers. They will need electrical engineers, they will need mechanical engineers, they will need computer scientists and things like that. And you look for such people. Yeah.
All in shell, we do not need to have a master's degree as a compulsion.
No. BTech, that's the magic of the engineering degrees. The 4-year BTech is considered to be an entry-level thing for PhD programs. And so you can, but then if you are going to work on a problem which will require you to know a lot of astronomy, then you might have to do. That's why I said master's degrees all over the world are taken as devices to switch from one subject to another. So if you, for example, want to work on an astronomical project, which requires a lot of astronomical training in addition to your engineering, then you better do a master's degree in astronomy as a kind of bridge course, right? And then you get into. So we had one of our lead mechanical engineers who were working on our Aditya L1 mission. He just last year left and went to the University of Arizona to do such a bridge course, a master's degree which will allow him to do generic astronomical instrumentation in similar subjects. And so he said, I don't know enough astronomy. I know a lot of mechanical engineering. I actually want to completely concentrate on astronomical instrumentation. So he's doing a master's degree. So then you have to think about the kind of, and so I'm sure there are people around you who can guide you with this to choose the right course, and then you make that switch.
Thank you so much, sir. That was really a wonderful advice.
Okay, Ayush, thank you very much. I mean, the only little thing I would add to what Shomak has very nicely and elaborately described is that from what I've seen also in IUCAA as well as NCRA, is that if you have an engineering background and want to do physics, one is of course a bridge course option which you mentioned. The other, even during your regular study now, you can sort of make sure that you're up to date in your basic physics. For example, if you want to do astrophysics, even with an engineering background, and as you mentioned, many of my colleagues have actually come with engineering background, done physics as they were doing engineering well, and have qualified, come to the interviews and have done well. So there are umpteen examples of that type. So just see what you're interested in and keep that interest alive. Study hard and brush up on the basics of whatever you want to pursue. So we'll go to the next person, which is Vaibhav Srivastav. Can you unmute yourself? Okay, fantastic.
Good evening, sir. Can you hear me? Hello.
We can hear you, but you're a bit soft actually. If you get
so
your
is it better now?
It's better now, yeah.
Yes, sir. So the question was actually regarding the PhD coursework which we'll be having before the PhD program. We have not had any formal introduction to astronomy in the integrated MSc courses which we had. The only formal introduction was this particular summer school, or maybe some other summer school which we might do. So what are the kinds of courses we have in the coursework for the PhD coursework? Is it an extensive one or just the fundamental things?
No, the PhD coursework actually, because many of our students also come from engineering backgrounds, consists of both basic physics papers, subjects, as well as astronomy related papers. So it covers both and trains you to actually carry on research. Not only does it are there regular sort of courses, but there's also a project component where you work with one of the faculty members. So even if you haven't done astrophysics earlier, but have a good background in physics, maths, and want to pursue it, the graduate school actually will introduce you to quite a bit of it.
And so is it similar for all universities, be it in India or abroad?
It may not be similar for all universities.
Yes.
But at least in IUCAA, NCRA, TIFR, that would be true. Raman Research Institute, JAP program, the Joint Astronomy Program in Bangalore. But it may not be true of all universities.
Sir, I had another question. Can I ask?
Sure, please.
So when we are applying for PhD and we would be going for interviews someday, what actually should we be prepared with? Because often internships are given a priority, but with such competitions around, internships are very rare. And for us, when we are going for PhDs, it would already be 2 years of quarantine, I guess. So we have already lost those opportunities. How much of importance is given to education, or is it the fundamental knowledge of physics which is given importance?
See, most of our interviews generally try to probe how much you know of the subject which you're supposed to know. And it's not the number of summer schools attended or internships that you have taken, because you may attend a lot of them and not learn very much. But obviously, if you do an internship, I mean, this pandemic era is obviously challenging and very difficult to do internships. But the interviews will basically test your knowledge of the subject, of what you have done in your undergraduate and postgraduate period, and how well you know that. Yeah.
Thanks, sir. So I had just one small follow-up, if you don't mind.
Okay.
So it was regarding, so most of the professors here have done their PhDs or postdocs somewhere outside, and they have come back to India, and now yet they're working here. I would just like to know, how was the experience for both of these?
Well, there's a mixture of both actually. Many have done their PhDs here, many have done their PhDs outside.
Yes,
we have both categories in most of our research institutions. And ultimately, faculty selection is also based on what you have done. And it doesn't depend whether you've done your PhD either inside the country or outside the country.
Thanks a lot, sir. Thanks a lot.
Yeah. So we'll move on to Sanchari Biswas.
Yeah.
Okay, sorry, Chomak wants to add something.
I wanted to say something because I have to leave
Sure, please.
The LIGO India workshop that's going on.
Please, Shoma, please, yeah.
If that's all right, and Surud is here, and if you can, I just want to say bye to everybody. Thank you. It's been wonderful interacting with you. And I'm sure this question answer session will go on. If that ends and this is still going on, I'll come back. But otherwise, bye now. Thanks, and thanks, Dipanjan.
Thanks very much, Shoma. Thanks a lot. Take care. Bye. Okay. Sanchari Biswas, you have unmuted yourself. You could ask your question. Vaibhav,
yes, am I audible?
You're audible. Vaibhav, could you lower your hand, please? You've finished your question so that we know that you answered. Sanchari.
Yes, sir. So I'm a master's student and I'm very much interested in pursuing research in quantum gravity. So I actually asked the question in chat, and Shomak sir already replied that I should keep up my interest there. But then he said that we should go for PhD to some place where the menu is big. So I got confused there.
So Dipanjan, you want to take that?
Yeah, I think what Shomak said in both occasions does not really contradict each other. I think Shomak said that you should carry on your interest, and that is certainly true. But you should also choose a department where there are people working on the research area that you're working on. For example, IUCAA has Professor Padmanabhan who works on topics related to that, not exactly. But there are other faculties, but maybe there are other departments who have a stronger group of faculties and a stronger research group focused on that particular subject area. But I'm talking in general terms, not especially for this particular questions for quantum gravity. For example, if you're interested in, say, astroparticle physics, as somebody just said, look for a department where there are several people or a strong active research group working on that field. So that would be better for you for also a larger exposure in the field, because not everybody works on the same subject. So I think both the things that Shomak said are complementary and also true. And does that sort of help you, Sanchari, in addressing the question?
Yes, sir. Thank you. So I should go to some place where there is a bigger group of people doing the thing.
That is also helpful, because then also there's a richer environment of students. So each faculty, has the students, postdocs, and a research group. So there's more interaction that you have with that particular area. And if you are interested and devoted in that particular niche area as well, so it always helps that you gravitate towards a department that has more researchers working on that. You may not always find that. If it is a very niche topic, you may not find strong research groups, but you can always search for a place where people who are working on that. So I would say you have to coordinate your search of where you want to go next in a more judicious way.
Okay, thank you, sir. Thank you so much.
So thanks a lot, Dipanjan. So we'll move on. Sanchari, now Smriti Chawla, would you mute yourself?
Good afternoon, sir. I'm Smriti from Delhi University. I'm doing my master's and I'm in first year. Sir, I have done some project in condensed matter physics, but yes, I have a lot of interest in astrophysics, and I don't know how can I, switch from this, or how can I infuse the two fields together? Can you give some idea that I can take my condensed matter physics along with astrophysics? Is there an option in it?
It's an interesting question. So, Surud, you want to take it? I'll just try to distribute the questions. Surud, you're there?
Yes.
Take that? Or?
Right, yeah. So you're saying you have a background in condensed matter physics, and so this is like a master's in condensed matter physics?
No, sir. So I am doing a project under a professor in SM Bose Institute.
Oh, I see. So it's just a project, right?
Research project, yes.
Your main degree would be something in physics.
Right? Physics, yes.
Yeah. So it's not a problem, right? As undergrads and so on, we have done projects in a variety of areas, right? It's like doing some kind of shopping, right? So if you have some research experience, that helps, because the methodology of research oftentimes is similar, right? and some people are made for these kind of aspects, right, where you have to define your own problems, come up with your own solutions, etc. So that part remains the same, right? So that's good. But in addition, if you can show that you have had some interest in astrophysics, you have taken up certain amount of courses, or you have also tried to approach some other people for particular projects related to your field, then it will also help, right? So I would suggest like taking that research experience from your condensed matter background and then also trying to channel it to some other projects in astrophysics that you could do.
So, like, is there any field of study, like I can study on something that includes the condensed matter theories, or like?
Sykes, let me just quickly add on to what Surud was saying. So I just wanted to, in response to these questions, remind the participants that astrophysics is almost like an application of all branches of fundamental physics. So you have particle physics, which we call astroparticle physics, but it's basically understanding applications of particle physics to understand astrophysical phenomena. Similarly, material science as well as condensed matter physics also has interesting applications in various branches of astronomy. For example, if you're working on neutron stars, if you're working on the crustal composition of neutron stars, there we do have to understand phonon-phonon scattering and all sorts of standard condensed matter stuff that you have learned in Kittel and Ashcroft. Those come in. So I'm just giving you an example. It's not that you would actually end up working on neutron stars to understand condensed matter physics. You might actually just take what Surud said, take your research methodology that you've developed and apply it something else. But if you are looking for applications of a particular field of science, you're really interested in that, you'll certainly find some area of astronomy and astrophysics that incorporates that. For example, even material physics. We need to understand how dust grain forms at different regions. We need to understand spallations of dust grains, interactions of dust grains with other particles. All these are part of material science as well. So I would strongly suggest that if you are strongly interested in some field, look for the complementary application in astrophysics, and I'm certainly sure you'll find it. And for condensed matter physics, as I have given an example, neutron stars and dense objects, we regularly apply those kind of things. I'm sure there may be other applications as well, which I'm missing.
Yes, thank you so much.
Thanks. Now we'll move on to Ditsa Sen. Can you unmute yourself?
Yeah, yes, am I audible?
You're audible, yeah.
Okay, so thank you. Sir, I am currently pursuing my master's in maths.
Okay.
So I have and had applied to certain internships or written to several institutions here as well as abroad regarding internships and maybe a future PhD in this field of astrophysics. And some of them have said that they will be open to taking students from a maths background, but only if my application is compatible or equivalent to that from someone who is from a physics background. So how do I exactly strengthen my CV or my application or my knowledge of physics so that it becomes similar to someone who's from math, who's from physics?
I couldn't, because of the range, I couldn't completely hear your question. What you're saying is that you're a math student and you want to apply for internship abroad, and they want this background.
Yes, sir. So internships or a PhD. So both actually. So some institutions have said that they are not open to taking students from maths, while others have said that they are open to looking at my application, but my application needs to be on a similar level as that of someone from a physics background. So how do I improve my application or my CV, or what are the things that I need to remember while applying so that, or my knowledge of physics, so that my application can become equivalent to that of someone from physics?
See, without knowing all the details, it's difficult to say, but what I would sort of instinctively feel is that if they're saying that, you should highlight the physics courses you have done, and hopefully you have got good grades in them, and that is probably the only way they would be able to judge the applications. Or reference letters from your physics teachers to sort of certify or talk about how well you know your physics, if they are asking for people with good knowledge of physics. So if you haven't done any physics courses, it's going to be difficult, but I think that is what my initial gut reaction would be. Would any of you like to add anything to it? Samir, Surud or Dipanjan?
Yeah, hi, Ditsa. I sort of know your case because we've interacted before. I think I would reiterate what I had mentioned to you earlier in our email exchanges, is that IUCAA also accepts candidates with applied mathematics in their masters. Right? So the thing is, technically, it's not stopping you from applying to any of these entrance exams to take the entrance test. What you will find difficult is when you actually sit for the exam, a lot of the questions will be from basic physics. Yeah. So it completely, so if you want to do a PhD in India and go through these various exams, you have to just brush up and learn, if you have not taken those courses, all the basic physics. And I'll also reiterate to all the candidates, the young students who are here, in the interview panels, we really do not ask you to derive very complicated equations. But what we really want to check is how good your fundamentals are. Because no matter what kind of complicated project or internship you've done, what is important for you to have a broad understanding of the fundamental physics, which is most often the BSc physics and the early first year MSc physics as well, which shapes so that when you encounter a completely new problem, you would have a solid foundation on which you can build on. And that is what we try to screen from the applicants. And this is what we would expect. So even if you have not gone through a proper physics course, as Ditsa, you have, your case is, if you have built up the knowledge and you can prove yourself in the recording in progress, that should be fine. But again, it completely depends on your self-study. Sykes, Suru, do you want to add anything to it?
I think what you have said is fine. Actually, Cyril, you want to add something to it?
No, I think that's great. Of course, the advice that you gave, Dipanjan.
But sir, just another question. If I apply abroad, as you said that since they often don't have a one-on-one interaction, so that's why they will be looking at my application, like maybe like the internships or my coding skills, etc.
Yeah, so this in that respect, as Professor Saikia mentioned, then if you have recommendation letters from astrophysicists or astronomers who you have worked with, that will certainly help you in the initial stage of screening. And of course, for any of these PhD positions also abroad, some groups also do take an interview. So you have to go through several levels of screening. And if you reach that final level, you'll also be screened based on the interview.
Yes, so just another tiny question. So if I don't have too many internship experiences or project experiences or papers published, etc. So how do I make up for that lack in that sphere with something else?
Well, you can always work on as a JRF or work on a project for some time and build up your expertise on that.
Yes, sir. Okay. Thank you.
Okay, thanks a lot. Yeah. So, Saikat Mazumdar, will you unmute yourself and ask your question?
Hello, am I audible, sir?
Yeah, you're audible.
Yeah, sir. So my first question is that I am a PSMS third year student currently. So when I apply to some professor or some institute for any project positions, any internship, some short-term summer or winter projects, so they generally say that they look for any prior research experience. So the thing is that since I am currently in my third year and this is the year where I have started taking my first major courses in physics. So right now the only experience I have are the courses only, right? So I mean, what should I do to get accepted in any project so that I can improve my experience in research so that I can further go about.
See, the only answer I could sort of advice I would give is that there are lots of faculty members who will take a student without previous experience, because obviously you've got to start somewhere to gain experience. But there are some who would actually try to look for some previous experience because of various issues which are legitimate. I mean, they may want to finish a project at a short time scale which they have at hand. They may want a certain level of expertise in a certain area, whereas others may not look for that. So my advice would be to actually, one thing is build up your profile in terms of your understanding your grades, and apply to a large number of persons to see somebody who would actually guide you through a project, whether it be a reading project or an experimental project, depending on your areas of interest. Because all of you have to start somewhere, right? Not everybody says that, I will not take a student without a project. So you have to try harder, write to a larger number of people, build up your profile in terms of your grades and courses. And also, people also look for, the overall sort of what your CV looks like. How are you committed academically? How does it come out through your CV? So those are aspects also which are important in terms of getting your first internship or first sort of project with a faculty member. Yeah.
Yeah, thank you, sir. And I have another question regarding IUCAA itself. So the thing is that I was asking what is the procedure to apply to IUCAA for a 5th year master's thesis?
Shrikant, I will refer you to the IUCAA webpage for this, and there are detailed instructions of how to apply for different programs. You can find all the relevant information there. Okay.
Okay, sure. Thank you, sir.
Aside, we have to move on, and we should try to.
What time do you want to wrap up? About
I think this will keep going on. So maybe the last question is Shubham, and we can stop there.
Okay.
Hello, sir. Am I audible?
Yeah, okay. Yeah, Shubham, go on. But I wanted to have Nandini first, maybe because there were others who had raised their hands before you. Okay.
Good evening, sir. Sir, I want to ask how I can take up astronomy after MSc Mathematics and not applied mathematics.
I think we already sort of responded to this.
Yeah, we responded to this question, I think, yeah.
Yeah, well, IUCAA has applied mathematics, but you can check with the IUCAA Academic Core Committee program. There's an email ID there with your query, and they can respond to that. Other universities will have their own sort of selection criteria. Okay. Anushka again has a question, but we've already responded to her. Maybe you go to Abhijit next, second.
Yeah, Abhijit Talukdar, I think. Yeah, we'll give it, Abhijit, you can answer.
Sir, I have a
Good afternoon, sir.
No, we'll go to Abhijit Talukdar with Anushka. You have asked your question earlier, and since you're short of time, we will give it a chance to Abhijit Talukdar.
Good afternoon, sir. Am I audible, sir?
Yeah, audible. Yeah, please go ahead.
Sir, basically, I have two questions. So, first of all, I am a first-year master student. So, in our university, we have specialization subjects in physics in the second year. So, basically, I am interested in the black hole physics. So, is it necessary that I should take up specialization in the subjects like high energy physics? Is it essential, sir?
See, in all these, as we have been stressing all along, most of these interviews or the ability to do research will depend upon how well you know your basics. Because once you know that well, you can build up. Definitely, taking high energy physics would help you if you want to, study phenomena using high energy physics. But I think as long as your basics are solid in physics and maths, you will have the competence to pick up whatever is required later. I mean, our students we have taken over the years have come from a variety of institutions across the country with different specializations, different backgrounds, and have gone up to do well. So whatever you find most exciting, you do. But what is most important is that you know your basics well and train yourself to actually know that as well as you can. Okay?
Yes, sir. Sir, basically, I have another question. So whenever we apply for some projects or even in the research, we have to, most of the time we have to pick up a problem. So sir, is the process like that? First we pick up the problem and then study, or we should be prepared beforehand on the topic and then go for these kinds of projects also?
See, a lot of it would depend upon the person you're working with. Okay. Very few people actually will ask a fresh student to come with a project. Okay, most of us try to sort of interact with a student, find out, provided we want to work, guide the student, find out what his interests are, what are his skills and what will he be capable of doing. And then we steer or go along together, doing a certain project. So your interests, your expertise, your guide's interests and expertise, all that will matter. Very few of us would expect you to come with a ready-made project. And if you have one, you have it in mind and the guide is willing, that's fine. But we normally don't expect that in most of the cases that I'm aware of. Okay?
Thank you, sir. Thank you, sir.
Okay, we'll probably take one last question and then we will stop. Okay, it's 5 o'clock right now. Nandini Sharma, Abhijit Arudra, Kaushik Bhanja. So will you unmute yourself? And this is the last one we'll take today. All right? That's okay, Dipanjan?
We should also give chance Shubham because we were speaking and I cut him off.
Okay, okay, Shubham and
Abhijit, we can take both of them.
Yeah. Okay.
Hello, sir. Am I audible? I'm Kaushik.
Yeah, please go ahead.
Yes, sir. Actually, my concern is that I have completed my master's in applied mathematics, having general relativity, cosmology as a special paper with differential geometry. My question is there any chance or opportunity available for my PhD position in IUCAA? Or if there is, then how can
Kaushik, we already responded to this with the same question from Ditsa. And as I said, you can apply to IUCAA and it will depend on how you respond in the interviews, okay? Technically, you can apply to IUCAA through these tests.
Sir, okay, sir. Actually, there is a trailing question. Sir, I have gone through the IUCAA website and I have found that you always require a net GRF in physics. But as a mathematics background student, I can only appear for the net GRF in mathematics. So how can I deal with this matter? Is there anything you can say?
You can also apply through the INAT exam, right? So it does not have to be the JRF always. So you can apply to the INAT and the IUCAA's own screening test. And for that, the eligibility criteria states on the website that applied mathematics is allowed.
Okay. Thank you so much, sir.
Okay.
Shubham, the last question.
Yes, sir. Sir, I wanted to ask how to deal with the rejection because I have been applying for many schools and many things, but people have been saying that your profile is not that good and the competition is being increased and you have to constantly improve yourself. And due to pandemic also, so many opportunities people have lost. So how to cope up with that?
Yeah, I mean, that's a hard one.
That's a hard one, yes.
I actually don't like anybody saying that your profile is not good because, we always go by the way of trying to encourage people to learn more and do better. So I wouldn't be able to sort of give you a direct answer to that, but except to sort of keep learning and trying,
Yeah, so I would also add to that, to prefer what Psyche is saying, is that as young students, we've also gone through this stage as you're talking about. And even at present, actually, the competition is really high. But I would sort of advise that please do not get discouraged. Rejection is part of life. We've all have received rejections at several different levels of life, as we have gone through different tests, different internships, etc. And opportunities are there if you search for them. And so it's all about you keep on searching, apply in volumes. Don't be very selective in your applications. Apply with all different places which you think will be suitable for you. And I hope that something turns up.
Dipanjan, there are only 2 hands up, so I think
maybe we can just sort of get to them as well. Yeah.
Shari Kapoor, can you unmute yourself?
Yeah. Good evening, sir. Am I audible?
Yeah, you're audible.
First of all, thank you for giving this opportunity, sir. I had this question that I'm working in plasma astrophysics right now. And I wanted to shift to like black holes and other fields of astrophysics and cosmology. So what should I do? I mean, also, what is the best way to convince a mentor to choose you as your project or research student?
Where are you working actually, Sherry?
So I'm from Amritsar, and I'm a student at Guru Nanak Dev University, but I'm working on plasma astrophysics under a doctor from a doctorate in plasma physics from Kolkata.
No, but at what stage are you? Are you master's student?
I'm a master's student. I have done my master's project in plasma physics, plasma astrophysics, and also a research paper I have is already published, and we are working on some more. So
that's very good, Sherry. But is it a master's in physics or is it a master's in plasma physics?
In physics, sir.
So if it's a master in physics, you can certainly apply to any of the PhD programs in astronomy, right? As we have already said. So there is if it's the fact that your plasma physics expertise is only at the level of a project for your master's level, so that does not really hinder you from applying to any other institute where there is general astronomy and astrophysics courses. I certainly am somebody who works on plasma astrophysics as well as computational astrophysics, as you might have seen on one of my lectures. So this is certainly good for me. But if you want to work on general astronomy, there's nothing stopping you. If you have a master's in physics, you can certainly apply to any of the institutes that take on students for PhDs in astronomy.
But sir, when we apply somewhere, what is the best way to convince the mentor to choose
a
student?
The best way to convince is you have your fundamentals in physics good, because you'll have to go through this interview process, right? For example, in IUCAA, you have to first pass the screening test, the written screening test in INAT or the JEST. And then you have to go through the interviews. So you don't really have to convince somebody that you've done something in plasma, but you want to work on something else. At the interviews, people might ask you on your project, but they can also ask you on your basic physics.
Also, sir, you told that there are many IUCAA associates all over India. So how do we know that which university or professor are IUCAA's associate?
Oh, IUCAA associates are different places, but you don't really need to know who are the IUCAA associates, right? You just need to look out for where some PhD position is available and then apply there. Then if the position is a targeted position, they're looking for a specific set of skill sets, you have to look at that. Otherwise, it's a general admission like in IUCAA, IIA, and several other astronomy institutes. They don't really target a specific skill set for that.
Thank you, sir. Thank you.
Actually, she may be referring to what Shomak said in the beginning about IUCAA associates guiding students, but that was not for a PhD. That was trying to do projects with them.
So I'm asking for the projects and research work only.
That actually we will try to put in place in our website. We are right now in the process of trying to put something along those lines in place. Depend on how many associates come forward to actually say that we will guide students interested in astronomy and astrophysics. And once that is in place, probably in a month or two, we will try and get the information across via website. But that is not for a PhD program. That is for doing short-term projects.
Yes, thank you, sir.
Okay, the last question, the last person, Vasudev. Then we'll stop here. Vasudev, you have your hands up. Are you there? Can you unmute yourself? Vasudev. Okay, Vasudev, go ahead with your question.
Anyone? I'm audible?
You're very soft though. If you can get closer to the mic.
I'm audible, sir?
You're better now. Yeah.
Still going on, my goodness.
This is the last question, Shomak.
Oh, good. I'm getting hungry. Go ahead.
First of all, thanks to the IUCAA, which we provide such opportunity to participate that summer school. It's an amazing experience for me. My question from the Dipanjan sir. Sir, there are most of lecture missing in the PB work site. Please make sure that all PPT and PDF will upload the sites. Thank you, sir. Thanks.
Thanks for your comment, Vasudev. We have received some of the slides from some of the lectures. We'll be in touch with others. Please look out on the PBWorks website. Some of them, as we get the lectures from the instructors, we'll upload them. The instructors are also busy with several other things, so you have to be a bit patient. Thank you.
Thank you, sir. Thank
you. Dipanjan, I want to mention a couple of things that have come up in the chat. And that is there was one chat where I was answering questions. People are talking about whether they can come and do PhD in astrophysics if they have a MSc in astrophysics. So I just wanted to say that in India, only one place gives MSc in astrophysics, and that's IIT Indore, which started a couple of years ago. And it's not really MSc just in astrophysics, but it's astrophysics and space sciences and all that mixed. But none of us have done MSc in astrophysics. In fact, astrophysics actually exists in very few places in India, even as a master's subject. A subject in a master's course, and none at bachelor's, whereas in many foreign universities you have. Now, I wanted to announce that from this year, hopefully, IUCAA and the University of Pune together starting an MSc program in physics and astrophysics, right? In which you do half physics degree at Pune University and half in IUCAA. That will be announced soon. I'm hoping that this will go ahead this year. We tried starting last year, but of course, because of the pandemic, we couldn't. So keep an eye out for it. If you are an undergraduate who wants to do a master's, 2-year master's, the structure of the course will be half year. 1 year will be the same as physics MSc, but the second year completely will be astrophysics taught by IUCAA people, right? And so this I wanted to announce here because there are many undergraduates here. I hope this will happen, and only in the next few days we will know, because the way things are opening up, how admission tests will be done, how interviews will be done, we do not know yet, right? Certainly will happen next year, but it can happen this year as well. Other than that, there is no such plan that I know anywhere of having a master's in astrophysics. So one of the summaries of today's discussion is that we need people from physics, mathematics, statistics, and engineering to come into astrophysics. And so if you've done a master's degree and an advanced degree in any of these, or a bachelor's degree in any of the engineering, you can sit for any of these exams and come into the PhD system, not just at IUCAA, but any of the institutes that offer. So that's something I wanted to add to this discussion today. And thanks. I mean, I don't know whether anybody else has anything else to say. Final words.
Yeah, I think we can close now. Thanks very much to all of you for participating in this discussion today, and wish you all the best with your careers, and stay safe, what you do, and best wishes. Panjan, Shomak, you want to say anything else?
No, that's just the same thing. Thanks for attending. Thanks for staying with us for the 1 month experience. And it was very nice for us to also organize this lecture series. And all the instructors really put in a lot of effort and work in spite of the challenges posed to us by the pandemic. And I'm also glad that this was helpful to some of you. So thank you again. And I hope that you'll again join us for the subsequent things that IUCAA organizes. Shomak, any last words before we sign off?
No, thanks. I really enjoyed this experience, and I hope we've created a few astronomers today. Thank you.
Okay, thanks a lot. Bye.
Bye, everybody.
Bye.